Media tanks, also known as sand media filters, are pressure tanks filled with some type of sand-sized particles. They are the most popular form of filtration for drip and microirrigation for situations of a high dirt load of organic and/or inorganic material. The depth of the media provides a three-dimensional screening-like process that has much more debris storage capability than screens. In order to get the full benefit of media tank filtration, one must pay attention to the proper number and size of tanks, the proper media to place in tanks, installation procedures, adjustment of the backflush, special auxiliary hardware, and design details of the tanks themselves. Media tanks are designed with four basic components: the tanks, the media, the underdrain, and the backflush hardware. A minimum of 2 tanks are required so that clean water is always available for backflushing. At least 3 tanks are recommended. Tanks typically come in 12 to 48-inch diameters. For very large flow rates, many 48-inch tanks will be installed in parallel. Each tank has an equal amount of water flowing through it. For a 3-tank system during normal filtration, 1/3 of the water will flow through each tank. Each media tank is filled with sand-sized particles. This media, usually crushed granite or silica, provides the filtration and has a bed depth of about 14 inches. Tanks are flushed frequently enough so that the majority of the debris is captured within the top 4 inches of the media bed. An underdrain is at the bottom of each tank. It allows clean water to exit the filter tank. Holes or slots in the underdrain are small enough to prevent the media from exiting the tank along with the clean water. The underdrain performs another important function during the reverse flow backflush cycle. It then distributes the backflush water evenly throughout the media bed. The backflush hardware starts with a 3-way valve. It either lets dirty water into the tank from the inlet manifold or stops that flow and opens a connection between the tank and the backflush manifold. Other necessary hardware includes air vents and pressure relief valves, backflush adjustment valves and piping, and other devices mentioned later. During the filtration process, dirty water enters into the tank from the top. Remember that if there is a 3-tank system, 1/3 of the water flows through each tank. The water enters through a 3-way valve, which is then later repositioned during backflushing. After passing through the 3-way valve, water hits diffuser plates, which help distribute the water evenly over the top of the sand media. Then the water passes through the media, leaving behind the large organic and inorganic materials within the media. After passing through the underdrain to the outlet, the water enters the outlet manifold pipes and then goes to the irrigation system. The backflush process is the most critical part of the operation. Backflush hardware and adjustments are the most crucial aspects of successful media filter operation. During the backflushing process, only 1 tank at a time is backflushed. For a 3-tank system, the other 2 tanks will supply clean water to the tank being backflushed, plus they supply water to the irrigation system. To initiate a backflush, the 3-way valve at the top of 1 tank is turned to shut off the incoming flow and to open a path between the tank and the backflush manifold. During backflushing of a tank, some of the clean water enters the underdrain from the outlet manifold. This reversed flow passes upward through the media bed and actually fluidizes the media by lifting it up. Contaminants are purged through the top of the filter and exit via a special backflush manifold. The basic operation of the media tank are to first filter the water and to then backflush to clean the media. In order to do these 2 functions properly, one must pay close attention to many details related to hardware and adjustment. The optimum size and number of tanks are based on the irrigation system flow rate. This table shows examples of the recommended number and size based on the flow rate in gallons per minute. For example, for a 700 gallons per minute flow rate, it is recommended to use 3 48-inch diameter tanks. Notice that a minimum of 3 tanks is virtually always recommended, although many field installations only have 2 tanks. If only 2 tanks are used, during backflush, the 1 tank not only carries all of the system flow, but the backflush flow as well. In other words, if you have 2 48-inch tanks with a total flow rate of 500 gallons per minute, during normal filtration, the flow rate through each tank would be 250 gallons per minute. When the tanks go into the backflush mode, 1 tank must filter the 500 gallons per minute flow rate of the irrigation system, plus provide the extra flow rate needed for the backflush of the other tank. The backflush flow rates for various tank sizes are shown in this table. A 48-inch tank has a backflush flow rate of 190 gallons per minute. This means that the 1 filtering tank will have a flow of 500 GPM for the irrigation system, plus 190 GPM for the backflushing tank, for a total flow rate of 690 GPM. The flow rate for this 1 tank will more than double. This will scour sand away from the sides of the tank and also cause a large pressure drop across the system. This extra pressure drop during backflushing usually causes the downstream flows and pressures to drop excessively. This table shows results from 2 possible filter configurations for a flow rate of 500 GPM. The bottom line shows that during backflushing, the 2-tank system has a flow rate of 54.8 gallons per minute per square foot of filtration area, whereas the properly sized 4-tank system has about half of that. As mentioned earlier, such a very high flow rate per square foot of surface area in the 2-tank system will cause a tremendous pressure drop across the filters. For example, if the 2-tank system has a normal pressure differential of 7 psi during backflushing, the pressure differential would increase to 50 psi. Since this is such a large pressure drop, what actually happens is the flow going into the irrigation system decreases substantially. In contrast, a 4-tank system that has a normal pressure differential of 7 psi would only increase its pressure differential to 11 psi during backflushing. This small additional pressure drop would only slightly affect the flow into the irrigation system. Selection of media is affected by the degree of filtration needed. Deciding the degree of filtration needed is a 2-step process. First, one must determine the mean filtration capability needed. Then, one must select the correct media for the mean filtration capability needed. The mean filtration capability needed is determined using a formula for either emitters or for micro sprinklers. For emitters, the formula is filtration needed equals the minimum emitter hole diameter divided by 10. For micro sprinklers, the equation is filtration needed equals the minimum sprayer hole diameter divided by 7. For example, an irrigation system having emitters with a minimum hole passageway diameter of 0.05 inches would need a filtration capacity of 0.005 inches. In metric, this is 0.127 millimeters. This table provides typical available media sizes and types for agricultural high flow rate media tanks. 0.47 millimeter crushed silica and 0.78 millimeter crushed granite are 2 widely used media type. Number 11 crushed granite is similar to number 16 crushed silica. This table shows that crushed granite or crushed silica are better than round sand as a media. This table also shows that the media number by itself does not indicate the degree of filtration which will be provided. A second consideration is the uniformity of the media. A good media uniformity coefficient is less than 1.5. For best results, one should specify the mean effective media size and a uniformity coefficient less than 1.5. Manufacturers have two primary underdrain designs: epoxy composite aggregate cakes and lateral or slotted underdrains. Within each design are various shaped materials and sizes. Epoxy composite aggregate cakes are poured into the bottom of the tanks. There are advantages and disadvantages to this type of underdrain. The advantages are even distribution of water across the bottom of the tank and a low pressure drop when clean. The disadvantages are these: pluggability. If the cake is plugged by incoming clay or algae, the cake must be removed and replaced rather than cleaned. Some restoration can occur with chlorine or acid baths. Fragility. If the epoxy drain pores become plugged during the backflush mode, the cake will have a high pressure differential across it with no upper support. During backflushing, the media is lifted and fluidized, and there is no top support on the epoxy cake to hold it down. Because of this, the cake can crack at the beginning of the backflush cycle, and there is the possible degradation of epoxy resin with time. Lateral or slotted underdrains have many variations. These include spokes of stainless steel well screen, which radiate out and upwards from the bottom of the tank, or vertical cylindrical ports on a pipe network. These ports may have stainless steel wedge wire with V-shaped slots to reduce particle entrapment, or plastic mushrooms, which are slotted and conical structures mounted on a steel floor plate near the bottom of the tank, or a grid of plastic pipes with slots or holes. A gravel pack is commonly used with lateral slotted underdrains. In general, washed crushed rock 1/2 to 3/4 inches in size is used for the gravel pack and covers 2 to 4 inches above the highest point of the underdrain. There are two purposes for this gravel pack. First, it supports the sand media and keeps it separated from the underdrain slot. And it also helps to disperse the backflush water flow evenly across the bottom of the media bed. These slotted underdrains have become popular because of their advantages. These advantages are durability and serviceability. There are disadvantages, however. The underdrain slots can plug up with media if the gravel pack is the wrong size or is not used. The underdrain slots can plug up with media if the slot sizes are not matched to the media size. One should note that some manufacturers use mechanical fasteners or spot weld the slots to the underdrain pipes. There can be problems with either the mechanical fasteners or the spot welds. The mechanical fasteners may vibrate loose or come loose during shipping. This can be easily checked by the installer. One should also check the quality of a weld. There are many types of tank materials and coatings. The most common tank materials are carbon steel or type 304 stainless. Some fiberglass tanks are also made. The primary material and coating considerations are corrosion and flaking or scaling of the metal or coatings. Uncoated carbon steel is subject to corrosion. Type 304 stainless steel is corrosion resistant but not rust-proof. Salt, chlorine, and alkaline water conditions can produce pitting in the metal, which can develop into pinhole leaks. Installing an anode inside the tank helps control electrolysis. If the salinity of the water is greater than 600 parts per million, it is highly recommended to use Type 316 stainless steel rather than 304 stainless. Various lining can be applied to the interior of the tanks to combat against flaking or scaling. Fusion epoxy internal lining, if done properly, is very effective against chipping, cracking, and corrosion, except in very low pH water conditions. Epoxy painted or brushed coatings are generally less durable than fusion epoxy internal lining. Note that even one chipped or uncovered spot invites rust and corrosion. There are 4 special concerns related to pressure ratings of tanks: the tank diameter, the tank wall thickness, speed of backflush valve closure, and the use of PVC piping to connect the tanks. First, large standard tanks have lower pressure ratings than small tanks. For example, typical pressure ratings are shown in this table. A small 18-inch diameter tank has a large 125 psi pressure rating. A larger standard 48-inch tank has only a pressure rating of 80 psi. Material thickness of the tanks differ from one manufacturer to another. They vary from 3 to 5 millimeter. Fast closure of backflush valves can cause large pressure surges. Attention must be paid to the use of exterior PVC manifolds, as the pressure ratings change with respect to changes in temperature. At a temperature of 100 degrees Fahrenheit, PVC nominally rated at 100 psi working pressure must be derated to 62 psi working pressure. This figure illustrates the proper types and locations of various accessories needed for media tanks. There are many essential accessories for the media tanks. These include the backflush flow rate adjustment valve or backflush flow rate restrictor. This valve can be a gate, butterfly, or globe valve located downstream of backflow manifold after the last media tank. This valve is an essential item because the flow rate of the backflush water will blow all of the media out of the tanks if the flow rate is too high. Conversely, if the flow rate is too low, there will be insufficient lifting and cleaning of the media during backflush. This valve, then, enables the operator to adjust the backflush flow rate. Once this valve is adjusted for the proper flow rate, the handle should be removed to prevent later misadjustment. Sight glasses are used so that drip system operators can see the quality of the media tank backflush water. The backflushing should continue until the backflush water looks clean. The sight glasses must be conveniently placed and easy to see. There are 2 types of sighting glasses in the backflush line. One is a specially designed sighting and sampling port, which continually passes a portion of the backflush flow through a small attached glass jar which allows an operator to see if sand is passing by. Another is a section of clear plastic tube, which allows the operator to see if the backflush water is dirty or clean. This tube should be kept covered to protect it from sunlight damage, except during backflushing. It is essential that the operator be able to take samples of the backflush water during the initial adjustment of the backflush flow control valve. That means the end of the pipe must be accessible. The flow control valve should be adjusted so that there is just a little bit of media leaving with the backflush water. By holding a screen under the open pipe discharge, one can see if sand is in the water. An air vent and vacuum relief valve should be located at the upstream end of the backflush manifold piping. This is especially important for filters with automatic backflush valves. The air vent helps release air from the flush-out line at the start of the backflushing, and also relieves the vacuum caused when the backflush line is shut off. It can eliminate noise or chatter from the backflush valves and prolong their life. A combination air vent, which includes continuous air release capabilities with vacuum relief, should be located at the downstream end of the supply manifold. It helps evacuate air from the piping and tanks when the system is being filled up with water and during operation. A 50 to 100 mesh basket screen captures any media which might inadvertently pass through the underdrain. It can also prevent catastrophic plugging in case an underdrain should rupture. A pressure relief valve is located upstream of the filters. It is used to protect the filters from overpressurization and damage from water hammer. A pressure sustaining valve is required on many systems. It is needed when the water supply cannot meet the flow rate to the system and to the filter during a backflush process. That scenario was discussed earlier in this video when it was suggested that 2 tank systems not be used. However, if a pressure sustaining valve is needed, one of the new low pressure loss designs should be selected. A rinse valve is necessary upstream of the filters for some installations. The rinse valve is only used during the initial cleaning and backflushing of the filters. Media and gravel, when purchased, often have a high percentage of fine particles which could pass through the tank under drains and into the irrigation system. It is necessary to clean the media and remove those fine particles before irrigation water is allowed to pass from the media tanks and into the irrigation system. The media is cleaned by shutting off a valve downstream of the media tanks and then opening the backflush valve to only one media tank at a time. In other words, the total flow into the media tanks will only equal the backflush water for one tank. The rinse valve is necessary if the pump is quite large, and if the pump will be damaged if the flow is reduced so much that only the backflush flow rate is discharged. Pressure gauges should be installed on both sides of the media tanks. As the media tanks get dirty, the pressure differential across the tanks builds up. Flow meters should be installed downstream of the media tanks, but upstream of any acid injection point. A pressure regulator is needed upstream of the filters for those cases in which there are different water sources with varying pressures. It helps to keep the backflush rates constant.